All right, so we got two types of charge, positive and negative, you guys already said. Like charges repel each other, so positive and positive repel, and negative and positive would attract each other. And in order to really understand what's going on with charge, we have to go like subatomic. We got to talk about electrons, protons, and neutrons. What charge does each one of those have? Positive, negative, but which ones? Protons are positive. Protons are positive. Electrons are negative. And neutrons we really don't care about because they're neutral. They don't do anything for us. They are entirely neutral. And remember that it's the electrons that can move. Our protons are locked in the nucleus. They can't move around. Those nuclei are locked together, but the electrons can move about. They can kind of do whatever they want. So whenever we're talking about electricity or charge happening, we're talking about a change in number of electrons on something. If you gain electrons, then you get negative charge. But if you lose electrons, it's kind of like having two negatives. You get less negative, so you get more positive. Can't really reach over there. I couldn't take a step. It was too much work. You know me. So, what? That would be weird if anyone's out there that's listening to this. Hello, my name is Mr. Merlenbach. I'm a physics teacher at Blue Valley High School. If you would like to recreate any of these videos, feel free to email me for licensing information. No. Anyway, so if we gain electrons, we get negative charge. If we lose electrons, we get positive charge. And most of... What's that? I got it for Christmas. Anyways, it's in the video now. I got this headset for Christmas. So... Kelly, what are you doing? You're sabotaging this. Sabotaging it. So, with all of these problems, especially the conceptual ones, the question becomes, where are my electrons going? That answers most of it. You can figure out where the electrons end up. You can tell a lot about what is happening. And remember that the electron is the smallest, or the proton, that sort of elementary charge is the least amount of charge that we can have. The elementary charge is on one electron or proton. Electron or proton. So we represent that as E, and for an electron it would be negative E because electrons have negative charge, and protons would just be E. Unfortunately, it's not easy. It's nice. We can use the elementary charge to sort of count how many more protons or electrons we have, but we can't use that E as a unit in our calculations. We have to use coulombs. So let's say we had 150 protons, 700 neutrons, and 250 electrons. My first question is, what is my net charge? 12? It's not 12. It's not 12. The question is, how many more of which type do we have? 100. And it's electrons. So if we take our 150 protons, they have 150 elementary charges that are positive. And then to that we add all of those negative elementary charges. The negative 250, we get negative 100. It just means that we've got 100 more electrons than protons. And again, that's nice for just saying whether an object is positive or negative, but if we want an actual number that we can use in calculations, we have to say that 100 electrons is going to have to get converted.
Wait,
That is elementary charges. It's just a label. Not, no, no, this E is not your natural log E. That is just like a unit. So with the protons, they still have a charge of E, but electrons have a charge of negative E. That's why that negative has to be there for the electrons. All right. Correct. Protons and electrons have the exact same amount of charge on each individual one, but they're just different signs. One's positive, one's negative. So if we're going to convert this to coulombs, that is 1.602 times 10 to the negative 19th coulombs. That number will be given to you. I'm not expecting you to memorize that. But you do need both of the equations that I'll get back up here at the end to be memorized. I'm not going to give you those. And this should come out to be 1.6 times 10 to the negative 17th negative coulombs, if you do the math there. Yes, it's over 1e, because then those e's cancel out, and this was an equality that we had. One electron has that much charge on it. It is just like stoichiometry if you're a chemistry person. Some people are not. Some people are not, I've learned. One of the biggest ideas that we can have is that charge is conserved. We don't lose electrons anywhere. There are a certain number of electrons in the universe right now. That number is going to stay the same. And there's nothing you can do about that. You can't destroy or create those electrons. Again, if we gain electrons, it makes it more negative. And if we lose electrons, it's more positive. Those electrons have to come from somewhere. Again, track your electrons, and oftentimes for the conceptual problems, that's going to get you the answer. One of the biggest ideas with this was for where we had two identical objects. If our objects are identical and they touch, what are they going to do with the charge? Split it how? Equally, perfectly equally if they are identical. So let's say we had a positive 2 charge on one object, and the same object, a different one, had negative 4 charge. They have an overall charge of this negative 2 coulombs. So then if we split that negative 2 equally, they each get 1. Double check yourself with some of those more intense ones where we're touching, this object to one and then another object to another, and all those. A couple of those will be on the test. Those are intense. And with that same idea with conserved charge, before I move on, what type of transfer of charge was that? If we touch something, what do we call that? Conduction. Contact sounds like conduct, sort of. Not great, but it's better. They both start with C. It's the same. It's with con, like chili con carne. It's like chili with meat. Word. I'm more of a con queso man myself. I like the cheese. What's that? So, one of the ways that we represent this idea is with diagrams of electroscopes. With diagrams of electroscopes, we start off with a neutral electroscope. That's that little box that never worked for 7th hour. So, right. Did it really? He also dropped one a different hour, so it's all right.
He also just straight up grabbed the sphere, no hesitation. He was like, boom. Yeah.
So, if I bring in a positive charge, a very positively charged object, we've been on this whole time. I'm not pausing it. This is stream of consciousness YouTube. No editing, that's for wimps. So, what? So, if you bring this positive charge near that object, if I just bring this positive charge up close, where are the electrons going to go?
To the large object.
To the large object. These electrons down here are like, hey man, I want to get a little piece of that action. Like it's nice. I like that positive charge. We're going to move on up. And we get what is called charge separation. When we get a region that is very positive and a region that is very negative. So this whole section is very positive. This whole section is very negative. There's still protons up here, but now there are just more electrons. So we get a negative region. This is charge separation. If you're going to draw, the diagrams, and you just put negative and positive as your diagram, that's fine. That's actually what you should draw because we've got so many more electrons up top now. And if we do this, we can actually now charge by induction as well. I know I gave you the steps to that in the notes, but I just want to run over them.
Wait, is that the result?
This is the result of it just coming near it. Yes, on the right is the result.
Is deduction, deduction a thing? Or is that English?
That's English. So if I then take this very positive object away, it'll return to being neutral. But I can charge it by induction, which is one extra step, to get it to stay.
Wait, these things are the grounded?
Yes, and that's where we have the grounded piece of this. So whenever I ground an object, I make it as neutral as possible. That's what grounding does. It either gives you electrons or takes away electrons to make your object neutral. So if I've got this object like this, and I come in and I touch right here to the ground, am I going to add electrons or take away electrons? Add. I want to balance out this very positive section. I want to balance that out. These electrons are like, we need to get right there. And after I unground it again, so I disconnect it from the Earth so I can't lose any of those electrons, and I remove my object, then overall I would have more electrons than protons because I added some and didn't actually take away any. And with doing that, we end up with a negatively charged overall object. So when we charge by induction, we switch the charges. If I bring a positive charge, then I end up with a negatively charged object afterwards. So charge by induction, switch the charges. So I brought a positively charged object. My object became negatively charged.
So that's induction.
That is induction. Conduction is slightly different. Do we still need a second to write this?
Yeah.
Okay, I'll just talk to the fine people of YouTube for a couple minutes. Hope you're all having a fantastic day. I'm not talking to the class right now. I don't care about them. No. What's that? So, if instead I charge by conduction, it's slightly different. So let's say I had a very positive object. Actually, I'll make it negative so my analogy works a little bit better. It's very negative. I got a good. So I got a very negative object, and I bring it next to an electroscope. That is neutral. There we go. Think of the charged object like you during a tornado drill. Unfortunately, these classrooms are used for the tornado drills.
Unfortunately.
Yes. As nice as it is to know that I'm going to be safe, the fact that like 200 people are packed in here, not really my thing. Especially when they're freshmen. And they all smell like way too much Axe body spray. Like it's, find a balance, guys. What's that? They're in like biology now. They got a couple. They'll forget it. It's not about them. The freshmen are awesome when they're seniors and juniors. I don't know. We'll see. But imagine that this very negatively charged object is like one of these classrooms during or tornado drill. It's packed. It's super uncomfortable. You have to like stand next to people and like maybe your shoulders touch. It's like, I don't want to touch them. But the second the door opens, everybody just like pours out, right? They're like, yes, finally, boom, out the door. The hallways are still a little bit crowded, but it's better than being in the classroom. That's the same way with these electrons. When they get in contact, that's like the door opening for them. And yeah, it's already kind of crowded in the electroscope, like it's perfectly balanced, but they're like, even if we crowd that up a little bit, it's better than being here, right? So the electrons move across and make this negative. Some of the electrons get lost here. So they both end up negative. The large object is going to lose a little bit of its charge, but it'll stay negative. And this one will gain negative charge. So when you charge by conduction, you keep the charge. Both objects end up with the same charge with charging by conduction. Whether that's positive or negative depends. She
Yeah, that's
is.
me.
Apologize for that interruption. It was student council coming in. And I don't know. That was kind of sketchy, though.
Yeah.
We need to see you for a little bit. She left herself. She might be back. We can get the scoop. Oh.
I have to go, I guess.
For what?
I guess I'm nominated, so like I have to go have a meeting. For
Is there a
Sweetheart Royal?
pet?
I don't know.
I don't care. Okay.
Yeah,
All right. Cool. Charges conserved. That's old stuff. Oh my. So that takes care of everything really from the first section of the unit. That's the first 15 questions on the test in a nutshell. Again, make sure that you are comfortable with those concepts. Follow the electrons is the best thing you can do. This is an example problem. This is part of the next section of the unit, the actual equations stuff. Let me get there. So, force equals EQ. If you have a problem that says anything about electric field and has numbers, you have to use that equation. There's no other equation that we have. That's your go-to. And I wanted to clarify a little bit with the electric field stuff and the direction, picking out the direction. If you make sure that you assign a positive or negative sign to every single one of these terms, right? If I have a problem that says my electric force is upward, I'll make sure that that number is positive. My charge is negative, I make sure that I leave that negative in there. That will correspond to whatever direction the force is. They're all vectors, so they all get multiplied up well. So if I plug that in, I make sure that is my positive is upwards, I've got a negative charge. So when I get an answer of negative 300, that just means 300 in the negative direction. If up was positive, then down has to be negative. So keep that in mind when you do them. Include those signages. Include the signs. And a lot of the problems will just be plugging into that equation. That is Newtons per Coulomb up top. That's the unit for electric field. That's an up arrow. So, and with that, this idea of being downward or upward, there will be multiple choice questions where it would say 300 upward is an answer or 300 downward. For A and B, you have to be able to pick the right one. Awesome.
Are we gonna have to memorize K?
No, you don't have to memorize any of the constants. That'll just be given to you. Just really the equations. And the last one that we had was the force equals K Q1 Q2 over R squared. We did an example like this at the beginning of the hour, so I won't go through again. But I do want to hit on the idea of changing by a factor, right? If we double the mass, or I'm sorry, not the mass. Mass doesn't matter. Well, mass is matter, but Q, if we double the charge or double the distances, either way or change them somehow. So let's say for this one, we doubled both masses two times. I'm sorry, not mass. Doubled both charges, Q1 and Q2. And then we quadrupled the distance. We made the R 4 times as big. Our question then becomes, how much does the force change? So let me ask you this. Did we change K at all? No, we didn't change K at all. Both of our charges got doubled, so I put in 2's where they go. And our distance got quadrupled to be 4, but that has to be squared. Make sure you include the square in there. That's where people mess up. So we end up with 4 over 16 or 1 over 4. That means our force is now a fourth as big. If you increase the distance, you decrease the force. If you increase the charges, you increase the force. That and be able to do the calculations for the second half, and you are golden. And thus concludes the reviews. Have a good day, everybody.